Hi everyone, welcome back to chapter 24. In the previous video we defined our new term of electric potential, and another reminder, electric potential and electric potential are not the same thing. They are related to each other by the scalar value of our charge. And so we can go back and forth between the two definitions, but it is our main focus through this chapter to get a better definition of what electric potential is, how to measure it, and then once we know what that is, we can combine that information with our charge and see how the potential energy of the system changes, hence how much work is going to be done, and if we can work to move charges, that is going to be the foundation of everything that we do with circuits, because in circuits we're going to have electric charge passing through the different paths and branches of the circuit, and so we need to know how all of that works or how that happens. So what we need to do now is we need to consider a more generic system, and just to keep things as simple as possible, we'll consider an electric field with a charge that is moving through it, and that charge, we'll start it off right here, positive charge, and we will move that charge through the space to another location. So we have our initial location and our final location, and we already know that if we physically move a charge through the system will react by applying its own electric force, and we already know that electric force is going to depend on the electric field and the charge that we have. Well, we can see both of those there, but we're going to physically have to grab hold of that charge if we want to move it along that path. And so because, and I've drawn this path specifically with a curved line here, what we need to do is we need to consider at any point along that path the direction that that charge is being moved. And we've used ds as an infinitesimal displacement value in previous examples, so we'll go ahead and do that here as well. The fact of the matter is that as we move through space, that displacement vector is constantly changing its direction. And it is our job to figure out how much work is going to be done in this system, hence the change in potential energy, because that will tell us how much the electric potential in the system will change. And the reason I've crossed out that Q value is because the only difference that we have in the definitions of electric potential energy and electric potential is that charge value. And so putting everything back together from the previous video, we have the work minus the charge value as we move through the electric field in the system with respect to displacement, and that's going to tell us how much our electric potential changes, along with there's a minus sign in here that I forgot from the previous video, so that's our starting point. But as I said, we want this to be a more generic representation of what's happening, because here I have a constantly changing path. And we need to account for that. We need to account for any changes in the angle relationship between those two vectors. And that's where the cosine relationship comes in. So what we're going to do is we're going to basically go right back up to this expression. This is where we'll start. And we'll say that for every charge in the electric field that moves an infinitesimal amount of displacement, we will produce an infinitesimal amount of work. Right, so we're taking this expression up here and we're modifying it for what we need to do. But now that this has become an infinitesimal statement, it's pretty obvious that the only way that we're going to be able to account for the total work is if we do some integration. The integral of the left-hand side, we're just adding up all the work that's done, so that will become W. On the right-hand side, the charge that we're moving through space, we want that charge to maintain its value. So that charge is uniform. That value can come outside of the expression, which means we are left with this integral. And for any integral, we want to make sure that we have limits so that we have a definite outcome. Those limits are going to be the initial and final locations in space. We had a starting point. So there's an initial position associated with the particle when it's here, and there's some final position associated with the particle there. We need to integrate with respect to those values because it is the change in position as we travel through space, which is what we're integrating with respect to. Now, the last thing that we have to do in updating this is, if we remember in the previous video, we said that there was this minus sign. Oops, didn't need to erase that. There was this minus sign that showed up due to the fact that it is the system that is going to do work on us as we physically move the charge through space. And so we need to bring that minus sign down here. And we know that the work, or the negative work as we now have it, is responsible for the change in the potential energy of the system that we see. Potential energy, by definition, is charge times electric potential. Therefore, any change in potential energy will have to equal the charge times the change in the electric potential. And we're just going to use this as a substitute for the work term. So we now have Q delta V equals the same Q times the integral of our electric field as we travel through it. And now we can see that the charge that we've been dragging along through the math no longer matters. Because just like an electric field expression, we shouldn't need this charge to be present in order for the electric field to exist. We don't need that charge present in order for the field to operate and do things. So by that same line of thinking, got to bring that minus sign down. don't want to forget that. By that same line of thinking, we should be able to move through space and measure any changes in the electric potential. Later on, we can always bring that charge back and start taking measurements of changes in potential energy, work, etc. But what this tells us now is that we can basically bypass the requirement of having a charge present in the system. We can still do certain types of physics problems without the need of a charge to be present. And so this is going to be the generic starting point for all of the future expressions that we're going to derive to figure out the electric potential in a system. And I'm just moving the minus sign over to the other side because eventually it is the individual values of electric potential that we want to find as we move from one initial location to a final location. And these will be the corresponding potential values at those initial and final locations. Well, this setup with the calculus is only going to help us so far until we actually see an example problem in deriving the electric potential. So that's what we're going to do next. We're going to take this default expression for finding the change in electric potential for a system, and we will solve for it given a specific system of electric field. So the first thing to note is that we're going to need some kind of electric field expression that we can put inside that integral, let the calculus do its thing, and then we'll find out what the change in electric potential is. So let's start as easy as possible. Let's take the nicest electric field expression that we know of, and that is going to be the electric field that is produced by a single point charge. We know that for a positive charge, we will have electric field lines pointing out in all directions, and every point in space that is a distance of r will see the same magnitude of k, q over r squared. So we already know what the electric field is. Now we want to find out what is the electric potential at a given point in space. Well, our equation up here doesn't actually tell us that. The equation doesn't tell us what the electric potential is at a given point in space. It tells us what the difference in electric potential is between 2 points in space. So what we need to do is travel between two different locations in space, measure the difference in those potentials, and then see if maybe there's some way that we can identify what either of those individual values is going to be. So first thing first, we need to figure out just how are we going to travel through space. And what I want to do is I would prefer if we could travel along the radial direction. Right now, in order to get to this point in space, we would have to travel along the radial direction some value of r, and I want to know what the electric potential at that point in space is. It would really help if I knew what one of these values was going to be, and I can kind of do that. I can kind of cheat, because when I go to displace through space, if I were to go all the way out to infinity and then measure the electric potential again, well, the electric potential difference is going to be based on the electric field expression. What's going to happen to my field expression if I go way out to infinity? Well, my field's going to go to 0. And if my field goes to 0, there's no longer any force interaction, which means there's no more work that can happen. And if there's no more work, I can't change my potential energy anymore, which means I can't change my potential. And so through all of that argumentation, we can say that the electric potential out at infinity is going to be 0. And like in the previous video, we are now going to forcibly move from that 0 potential back to the point where we want to measure everything. And this now allows us to place values of initial and final potentials, essentially. So what we have here is we're going to have an initial position out at infinity, and we're going to have a final position at the R value, where we're actually trying to measure stuff. Okay, so all of this now has to go into our expression. We've already argued that the initial potential should be 0, and so all that's left is V final, but that's the potential value that I want to measure at the distance R. So we now have V equals negative I want to write all this stuff out before I say anything else there. Okay, so our potential at the point in space R is going to be the integral from infinity to R of our electric field as we move through space. And I'm going to make a confession right now. This is probably my least favorite of all of the chapters, just because I always have a tendency to lose a minus sign somewhere in my derivation, and so if I do that here, I apologize in advance. I'll do my best not to lose those minus signs, but if I do, I don't want to waste a whole lot of time trying to backtrack in the derivation, but I will show you what the end result of the derivation should be. But I also have my my class notes in front of me, so hopefully there shouldn't be any issues with this. Okay, here we go. I'm going to try this out. First, we're going to insert the expression for the electric field itself, and I'm just going to put in R and infinity for these limits. The electric field is 1 over 4 pi epsilon naught Q over R squared, and then we have that dot product with the ds. Let's take care of that dot product right now. Our electric field vector is pointing radially outward. So our electric field is pointing with respect to the point in space where we're trying to measure stuff. The electric field is pointing to the right. But our displacement vector, as we move back into the system, is moving in a direction that is opposite of that. So we need to put in a cosine relationship. We have E ds. So there's a cosine relationship between those two. And the angle relationship between those two is 180 degrees. And so we're going to get a -1 EDS. And, well, I already have E, I already have DS. The only thing that's left is to get rid of that dot product. But in doing so, it introduces a -1. I already have a minus sign out front, so now everything is positive. So that's always good if we can get rid of a minus sign along the way, and then we lose the vector notation there. Now it's time to remove any of the constants that we can from the integral. We can bring the q and the 4 pi epsilon out front, which leaves us with ds over r squared. Now we've already taken care of the angle relationship between E and ds, but now we have to integrate with respect to ds. And ds is not the same thing as r. The ds is traveling opposite the radial direction. And so that means that as we continue to move inward along each infinitesimal segment of ds, what we're really doing is we're moving backwards along the radial direction. And so my integral, which technically has two different variables in it, s and r, I need to rewrite it in terms of just one of those variables, and r actually makes far more sense than any of the others. And so now you can see where I often have problems trying to keep track of my minus signs, because we keep shifting back and forth between plus minus as we make these substitutions. Alright, so let's take that minus sign and we'll bring that out front so we can take care of the integration part. And it's not that bad of an integral. We have dr over r squared. If you prefer, we can bring the r squared term up into the numerator. And whenever we take the integral of a polynomial term, we add 1 to the power. Oops. We add 1 to the power, so that would become r to the minus 1. And then we divide by that new power. So that's the outcome for that particular integral. And if we rewrite this, that's going to turn this into a minus 1 over r, which, once we pair that with what we have out front, is yet another minus sign. So we could cancel those out, and we have Q over 4 pi epsilon naught 1 over R, and we have our limits, and I can't believe it. I think this is actually going to work. I think I managed to keep track of all my minus signs. So here we go. Keep in mind everything on the left should equal the final potential value that we're trying to get. And so now we plug in our limits. Our limit at R is just the term that we have in front of us, Q over 4 pi epsilon 1 over R, minus everything evaluated at infinity. Well, 1 over infinity is going to be 0, which, as we said, we should be getting the difference in the potentials for the system, but the initial potential way out at infinity was supposed to be 0. That's exactly what we're getting. And so the potential, a distance of r from our charged particle, is, let's see what we have here. We have Q, and we have 1 over 4 pi epsilon, that's K, but then we just have r to the first power. So let's, for the sake of comparison, the electric field that is being produced by this charge of Q is 1 over 4 pi r squared. But the electric potential that is being produced is kq over r to the first power. And, well, how does this relate back to the original expression that we had right here? We said if we have the electric field and we know how far we're going to go, does that give us the electric potential? Well, our electric field was kq over r squared, so that's E, and then D was how far we had to travel to get away from the charge itself, but that was R. And so then we get kq over r. And you might be thinking, well, you know, that was way easier to do and to set up to find the electric potential of a point charge. Couldn't we have just done that? And the answer is yes, as long as you are only displacing yourself along that nice straight line through space. The great thing about the electric field of our single point charge is that at any radial distance we are expecting a uniform electric field. Thus, at any radial distance of r, we should also be expecting to find a uniform electric potential value. I didn't draw this very well, so I'll try it again. So at any distance r from our charge, not only are we seeing a uniform electric field, but every point along the surface of this sphere will have the same electric potential value, and that value is equal to 1 over 4 pi epsilon q over r. So for a point charge, we have our electric potential value. And at this point we're thinking, okay, that's for a point charge. what else is there that we need to look at in terms of electric potentials? And the easy answer is everything that we've seen from previous chapters in terms of deriving electric field. We now need to take that information and use it to derive electric potential. But we now have a fairly standard starting point right here. If this is the electric potential that is going to be produced by a single point charge, remember, potential is a scalar. And when it comes to scalars, we can just add the numbers up. There is no fancy requirements for the summation or the integration. Thus, if I have a system of particles, and this might look familiar, if you remember back in the very first chapter for the semester, we had a system of particles with charges. We'll call them Q1, Q2, Q3, Q4. And we'll go ahead and put some measurements here on the number line. 1, 2, 3, 4, 5, 6. And we'll do 1, 2, 3, 4, 5. Just so it's not completely squared. And we can put some charge values in over here. We'll do 10 microcoulombs, -20, 30, and -40. The one major difference that we have with the point charge expression for potential is that we do not use the magnitude of the charge. We use the actual numerical value of that charge. So if I have a positive charge, I produce a positive potential. If I use a negative charge, I produce a negative potential. But those numbers can still just be added up. Okay, we have charges, we have positions along the number line. We'll go ahead and let our axes be in meters, just so we have nice units to work with. And we'll say that charge 2 is right there at the +5 mark on that y-axis. Back in chapter 21, we asked the question, what is the net electric field at a given point in space? And for that, we had to go through and use Coulomb's law along with some vector addition to put all of that together and get our answer. But now we're asking for a net electric potential. Those net electric potentials are scalars. And that's because we're going to be adding up individual potential values. And those values are scalars. There's no vector components. So electric potential doesn't care about direction. There are no vectors anymore. The only thing that electric potential is really going to care about is how much charge you have and how far away you are. That's it. Those are the only two things that we have to consider. The last question that we need to pose to ourselves is, where do we want to measure the net potential for this system? And I guess a nice spot might be right in the middle of that rectangular distribution of charges. I mean, we can ask for any point, it doesn't really matter. But now that we have a point, we can say, all right, I need to know what the electric potential at that location is that is produced by charge 1. I need to know how much potential charge 2 produces at that location, how much charge 3 produces, and how much charge 4 produces. Now, every one of these is a single charged particle producing potential at a given distance. Well, every one of these particles is the same distance from the center of that rectangle. We have a rectangle that is 6 by 5, and so each one of these R values right here would be, let's see, we've got 3 by 2.5, so R would be root of those. I'll have to put that in my calculator. Get my calculator app up and running. 2.5 squared plus 3 squared, and then we need a square root. And I'm getting 3.9 for the R value. So each charge has the same R value. Each charge is also going to have the same K value out front. The only difference is the individual charges themselves. So I'm going to write all this out. For V1, we have 1 over 4 pi epsilon Q1 over the common R value. For V2, we have 1 over 4 pi epsilon naught Q2 over the common R value. For V3, Q3 over the common R value, and then for V4, 1 over 4 pi epsilon Q4 over the common R value. And all those need to be added up. Obviously, the great thing about this is there's a lot that can be factored out. Because each charge is the same distance away from the center of that rectangle, we can factor out the R values. But if the charges were not the same distance away, then you would just have to keep those values paired up with the individual charges. But now it's just a matter of adding up the charge values, and we're pretty much done with this problem. We have 1 over 4 pi epsilon, there's R, and then we just have the sum of the charges in the system. Well, here's our charges. We've got 10 minus 20 plus 30 minus 40. And so that's, we've got a positive 40 and a negative 60, so there's a net charge of negative 20 for the entire system. Negative 20 microcoulombs. So this is the net potential at the center of that rectangular distribution of charge. Our 1 over 4 pi epsilon, remember that's just K. We can write that out using the value of K. We have 1 over R. R we calculated to be the 3.9. And we have our negative 20, 10 to the minus 6, because it's microcoulombs. And here we go. Let's see what we have. 8.99 times 10 to the 9 divided by 3.9. Oops. times 20 times 10 to the negative 6, and there's also a minus sign up front there, so I'm getting a negative 46,102 volts. So the fact that we have a negative potential at that location means that we can now take the next step in our problem, which is to insert a charge at that location. So maybe we insert a proton right at the center of that rectangle. If we do that, what will the potential energy of the system be? Well, I already know what the electric potential at that location is, so all I need to do is multiply that by the charge of the proton. And remember, from the previous video, we now have a choice in how we represent the energy of these particle systems. I can plug in the value of charge for a proton along with the voltage for that particular location. So I need to put in my 1.602 10 to the minus 19, and I'm getting 7.38 times 10 to the negative 15 with a minus sign in front of it. And in case you were wondering, yes, it is possible to have a negative potential energy. Just like up here, it is possible to have a negative potential. But as we said, there's another way to represent the energy, and that is to use the electron volt as your unit. The charge itself can be represented as some integer value of the elementary charge. Well, the proton uses one elementary charge value, and we've placed that proton into an area where the electric potential, or voltage as we might want to start calling it, is negative 46,102. And so what's the potential energy? Don't even need a calculator for this one. It's negative 46,102 electron volts. And these are equivalent energy values. They're just different units. But this is far easier to represent because we don't even have to do any math really. Well, let's go back. Let's take our proton and we'll replace it with an electron. So what is the potential energy of the system now? Well, an electron has a negative 1.602 10 to the minus 19 for charge. That combined with the negative potential is just going to cause for a positive potential energy. Likewise, in the second expression, the electron has a charge that is equal to negative 1 elementary charge, paired with the negative voltage of the system, provides a positive potential energy of 46,102 electron volts. So in this video, which I'm going to bring to a close here pretty quick, because if we continue on with any of the other derivations, we'll probably end up going over time. But the two things I want to take away from this are the default starting expression, which says that any change in electric potential can be found by taking the integral of the electric field as we move from one point in space to another. We use that to derive the electric potential for a single point charge. And then we were able to take that and use it in a fairly straightforward summation process, where we can find the net electric potential by adding up all the potentials for all of the charges in the system. But we have to think bigger. We have to think what's going to happen if we go from a system that involves 4 charges to a system that involves 4,000 charges, or 40,000 charges, or 4 million charges. We're not going to have all that time to add everything up, and so we need to figure out how are we going to take this expression along with the knowledge that we have about these two systems to find the electric potential for other distributions of charge. And so those distributions of charge that we're going to consider are the same distributions that we saw for electric fields. We're going to look at a line of charge. We'll need to look at a ring of charge. We'll need to look at a disk of charge. We're also going to look at spheres of charge, both conducting and insulating, solid and hollow. We might also need to consider cylinders of charge and what kind of electric potential they're going to produce. And we have to consider what those cylinders are made of. Are they conducting? Are they insulating? Are they solid? Are they hollow? And so all of these examples are things that we're going to look at in the next 2 videos. So I think we can probably get through these 3 examples in part 3, and then we'll do the spheres and the cylinders in part 4. And so from there we'll have a very good idea of how we're going to set up the electric potentials for any given system. And then we move on to the fun stuff, which is the circuits. And that's probably my favorite part of the semester, but we have to get through my least favorite part, which is setting up all the derivations for these electric potentials. But I've said it before, I'll say it again, you are not expected to reproduce the derivations, but you are expected to follow along the steps in the math and the logic and how it is that we get to the end results that we do. And then obviously you need to use those end results in your homework, your quizzes, and ultimately your tests. So we'll end it there, and I'll see you back for video 3.